Good morning, students. In the last class, we studied about work. We have given the definition of work and we have seen how we can measure work. We discussed two units. One is in SI system, that is Joule, and in CGS system, work is measured in erg. And this is what we learned. We discussed work is the product of force and displacement if the displacement is in the direction of applied force. Today we are going to discuss some more details about work. Now we'll see magnitude of work. We know magnitude of work done mainly depends on magnitude of force and displacement. The different possibilities are as follows. What are they? One is both force and displacement are in same direction. And the second one is force and displacement are opposite to each other. If they are opposite to each other, how we can calculate work? If force and displacement are in same direction, how we can calculate work? If they are in opposite direction, how we can calculate work? These things we will see. Next, the direction of force makes some angle with the direction of displacement. If force is in one direction and displacement is in another direction, then how we can calculate the amount of work done in that case. These things we will discuss. And one more thing, we are going to see work done against gravity. Against gravity, if you are doing some work, what is that amount of work done by you? That we can calculate. So these things we are going to see by using different formulas. We are going to see 4 different possibilities in our today's class. So now we'll see one by one. What are those? The first thing we know already, when force and displacement are in same direction. In the last class only we discussed, whenever they are in same direction, we can directly take the work as the product of force and displacement. Right? For this we are taking this example. We are taking one point A, and that point A, it reaches to point B when force F is applied, such that the displacement of the body is in the direction of force. Okay, you are able to see in this figure there is one body, and that body is initially at point A. We applied F amount of force, and because of that now body moved to point B. So the displacement of body in the direction of force is S. Now so we can calculate work just by taking the product of that force and the displacement in the direction of force. That is what we learned yesterday, that is W is equal to F into S. Right? Now we'll see some more points of different cases. Okay, we know if they are in same direction, this is the formula we are using, right? And if they are not in same direction, right? If they are not in same direction, then we are not going to use this formula. And one more thing, even though force is applied on it, but displacement of the body is 0, then automatically work done is 0. That is what we learned, right? Work done. So when we say work is done by applying force, if we give displacement to the body, then only it is said to be that work is done, right? But here displacement is 0, that's why work done is 0. And whenever force and displacement, applied force and displacement, both are in same direction, then that work done, we call it as positive work. Okay, sometimes they can ask a question, when work is said to be positive? If applied force and displacement are in same direction, we say that work is positive work, right? So we'll see example for this case. What example we can take? Here you are able to see one man is, right, when he is a lawn roller, when he is pushing the lawn roller, right, to level the pitch of a cricket ground. The force here applied by that man on the roller, and because of that, roller moves in the direction of applied force. So here force and displacement both are in same direction. Therefore, the work done is positive work here, right? Now we'll see one more case. If force and displacement are opposite to each other, So force is in one direction and displacement is exactly opposite in direction. Then how we can calculate that work done? Force is there, displacement is also there. That means definitely work is done. How we can calculate that work, right? So here we'll take this example. Let us assume there is one car, right? And that car is moving car. When it is moving, try to stop the car by applying some force. When we are applying force to stop the car, at the time, so we can see that force is applied towards right, but displacement of the car is towards left. So force and displacement are opposite to each other. So we can say that here displacement is negative. Why? Because it is moving opposite to the direction of applied force. So in this case, when you use the formula for work done, so force acting into displacement in opposite direction, that is W is equal to F into minus S. That means W is equal to minus Fs. That means this work we say negative work. So whenever you are applying force in one direction but body is getting displacement in the opposite direction, then the work done is negative work. W is equal to minus Fs, right? These things we have to keep in our mind. Suppose force is acting in one direction and displacement is not in the direction of force. It is not in the direction opposite to the applied force. It is in other direction. Then how we can calculate force? That we are taking this formula, right? Let us assume in this we are taking one toy. The toy is pulled using a string, right? That string I am taking it as OA, and the toy is pulled by using one string, right? In this case, toy moves horizontal. That means along OX. It is moving along OX. That is the direction of motion. But am I applying force along OX? No, I am not applying force along OX. The direction of force is along OA. You are able to see here. I am applying force along OA, right? So in this, force and displacement are not in same direction. Let us assume there is some angle between the applied force and the displacement of the toy. Let that angle is theta. Then how we can calculate this work? So in this case, work done we can take it as force into displacement into a cosine angle between applied force and displacement. How we are getting that? That we'll see. By using W is equal to Fs, we cannot get work in this case, right? Then what we are doing to calculate work done in this case, we are dividing force into two components, right? So when we divide force into two components, let us assume the magnitude of force in the direction of motion is F cos theta. So magnitude of force in the direction is F cos theta. So I am dividing force into two components, that is vertical component and horizontal component. The horizontal component of force that is in the direction of motion is F cos theta, right? So that theta to displacement, yes, I can take that as a work done in this case. Okay, you are able to see here force F is divided into two components, that is horizontal component Fh and vertical component is Fv. In the direction of displacement, the horizontal component is there, that is Fh. So if you know the value of Fh and you already know the displacement, you can get the work done in this case. So vertical component tries to lift the body, but it is not able to lift the body. That's why work done by vertical component is 0, right? There is no work done by the vertical component. Why? Because toy, so that vertical component is not able to lift the toy in upward direction. So the displacement in upward direction is 0. Therefore, I can say the work done by the vertical component is 0. Now, we are able to see there is a horizontal component, and that horizontal component is along OX and the displacement is also along OX. So to calculate that horizontal component, I am using this formula. What is that? We know, so right angle triangle, if we take by using Pythagoras theorem, we can calculate that one. So we know cosine or cos theta, We know already cos theta is always adjacent side by hypotenuse. So adjacent side in the figure is, you are able to see OX, and hypo is OA. Therefore, I can write it as FH by F. So where F is the applied force along OA, FH is the horizontal component that is along OX. From this, what is FH? FH will become F cos theta. So I got horizontal component of the force which is along OX, which is in the direction of displacement, that is F cos theta. Now I can calculate work. We know already work done W is magnitude of component of force into displacement. So component of force in the direction of displacement is F cos theta. So F cos theta into S. Therefore, in this case, the work done is W is equal to Fs cos theta. This is how we can calculate work in third case. This we can take it as general formula also. By taking angle, you can take this for any case. For case 1, case 2, case 3, for any case you can use this formula, right? So here, if force and displacement are in same direction, then angle will become 0 degrees. Cos 0 degrees is 1. Then W will become Fs. If the angle between force and displacement is 30 degrees, then we know cos 30 degrees is root 3 by 2. So we can substitute that value. We know cos 45 degrees, cos 60 degrees, cos 90 degrees, 0. This table, if you know, automatically you can decide how much work is done, even though force and displacement are not in same direction, right? Now we are going to take one more case, that is work done against gravity, right? So we know gravitational force always acts vertically downward. So in this example, you are able to see one box is on the ground and one boy is trying to lift that box. He is trying to lift the box in vertically upward direction, right? And this box, to lift vertically upward direction, he is applying force against gravity. We know gravitational force always acts vertically downward, but he is applying force opposite to that gravity. We know, so how much force he has to apply? The force required to lift the body or to lift the box will be equal to the weight of that body which is acting vertically downward, right? So here he is applying force against gravity. So the amount of work done, so in this case, will be equal to the product of weight of the body and the vertical distance through which the body is lifted. This is how we can calculate work. So what is this here? So weight is the gravitational force, but he is applying opposite to the gravitational force. And the displacement, the vertical displacement, let us assume the vertical displacement is h. Vertically he has taken to h height. So that I can say as a vertical distance or displacement h, right? And mass of the box, let us assume m. So then automatically what we can say, the force which you need to apply, that is equal to weight of the body mg, right? Now work done. So the force is applied in upward direction and the displacement is also in upward direction. Therefore, the positive work is done, and that work is weight of the body into vertical distance. That is, we know weight already mg and the vertical distance is h. Therefore, work done is mgh. Here you are able to see small g. What is small g? Small g is acceleration due to gravity. So we know already m is the mass of the body and h is the vertical distance. Okay, whenever work is done against gravity, the acceleration due to gravity, we are taking it as minus g. Okay, whereas the magnitude of work is always positive. I already told in the last class, work is the scalar quantity. It is having only magnitude. We know magnitude always we take positive. That's why magnitude of work is always positive, even though we are taking g as a negative one. Why we are taking g negative? Because acceleration due to gravity always is towards the center of the earth, but we are lifting the body against the gravity. Therefore, we are taking g value as minus g. Okay, this is how we can take work done against gravity, right? So one suitcase, you are able to see, is lifted from the ground to some height. So work done here, that we can say work is done against gravity, right? And now we are going to see zero work. This is also one kind of work, or we will see this zero work in the next class. Okay, thank you.